post-graduation at Utkal University, Bhubaneshwar, and PhD at Institute of Indian Institute of Astrophysics in Bangalore, and then had several postdoc positions, including University of California, Georgetown. I see a big list over there. Had a brief spell in IIT Guwahati, um, about maybe not a very brief spell, significant number of years, and then moved on to NISER, Bhubaneshwar. We know each other. We've been running into several conferences, uh, kind of thing. So I take over, and he's going to start off his talk. Thank you.
Thanks. Thanks, Ashok, for this nice introduction. And good afternoon, all. Let me share my screen first and see whether it is working. Yeah. So is it visible, Ashok? Hello?
Yeah, it's visible. It's visible. Go ahead.
Okay. Okay, so let me begin by thanking the organizer for inviting me to present our work in this conference. It seems to be a very nice meeting altogether. And today I'll be talking about some of our work which is not so recent, because as Ashok said, I just moved to NISER recently, last month. Actually, I finished 1 month here in NISER. So things are very tight at this moment. So Professor Paningrai asked me to present something more pedagogical for students. So I'll be talking something about our past work, like 2020, just 2 years back. We did something on quantum walk, and we tried to understand many-body quantum phases using the physics of quantum walk, which is rather a few particle problem. So in this talk, I'll give you two different topics, ideas about two different things. One is quantum phases of interacting bosons. So these are many-body systems. And then I'll show how quantum walk, which is a few particle dynamics, can actually capture this many-body physics. So this topic of quantum walk has been a very interesting or very demanding field of research at the moment, because it has various possible applications in quantum technologies. Apart from that, since it is a few particle dynamical process, these methods have been used to understand many different quantum phases in experiments. Okay, so both theoretically and experimentally, it is easier compared to the many-body problem. So as I go along, I'll discuss various things, and if you have questions, please feel free to stop and ask me questions. Okay, so this is the brief outline of the talk. I'll first discuss about the quantum phases of bosons in periodic potentials. These are very interesting topics of research because they have direct experimental access in various platforms. So in this context, I'll show you the role of multi-body interactions of bosons. And then I'll discuss about the physics that we obtain called the repulsively bound pairs. And then I'll show how these repulsively bound pairs can be simulated using the quantum walk. And then I'll conclude. So this is a fairly old topic of research, which is bosons in periodic potential. It all started in the year 1989 when people study the physics of this interacting bosons in periodic potentials. And you can here in a cartoon picture, you can see that this is a one-dimensional lattice or one-dimensional periodic potential. And I have shown these red balls as bosons. And since they are bosons, they can follow bosonic statistics. You can have any number of atoms, bosons sitting in different lattice sites. And they can actually freely move around, and this number can fluctuate. And you can see that different configurations of bosonic distribution in this lattice or in this periodic potential. So since these bosons can be non-interacting or they can be interacting, So depending on the situation, you can have the model that describes this system is known as this famous Bose-Hubbard-Hamiltonian. And this is very similar to your well-known Fermi-Hubbard Hamiltonian, except here instead of fermions, you have bosons, and you can have more than one boson at a single site. So in this Hamiltonian, you can see that there are two important terms. One is this hopping or kinetic energy term to the nearest neighbor sites. If you just assume that bosons are hopping to the nearest neighbor sites, and this is known as the hopping term. And this one is the two-body on-site interaction term. So if you assume that bosons are actually interacting with each other when you have, with two-body interaction, not higher body interaction. So this is the two-body interaction. And this competition between this T and U results in interesting physics. And this has been very well studied. And you can see that here I have shown this cartoon picture in a two-dimensional lattice. When this T over U ratio is very, very large, that means T dominates, the kinetic energy dominates, then these bosons can easily tunnel to different sites, and there is a long-range coherence between these bosonic wave functions. And there are this random distribution of bosons in this lattice, and this is a gapless phase, which is known as a superfluid phase. But if you go to this other extreme where this interaction is very, very strong compared to this kinetic energy, then you can see that every site is occupied by this single atom, single boson. If the densities, the number of bosons are same as number of lattice sites, then you can have a situation where there is no number fluctuation and the tunneling is suppressed because this interaction is very, very strong. So one boson cannot allow the other boson to come and sit on top of it. So therefore, this is a gap phase known as this Mott insulator phase. So there is one extreme here, which is a superfluid state. The other extreme is an insulating state. And if you tune this parameter T over U, there exists a phase transition, which is a quantum phase transition because we are considering zero temperature at this phase. Okay, so you can go from one extreme to other extreme through a phase transition point by tuning this ratio T over U. And it was first predicted by a group of Matthew Fisher in 1989. And then following this by a group of, the paper by Jacques et al., they proposed the experiment of this phase transition in optical lattice systems. And it was first actually observed in a system of cold atoms in optical lattice in the group of Emmanuel Bloch. So if you look at the phase diagram, the gist of this model and the solution of this model, this is the quantum phase diagram of this model. This is a mean field phase diagram where you can see that this axis is this tuning parameter T over U, and this axis is the chemical potential, which decides the number of particles in the system. You can see that these lobes are the Mott insulating lobes. These are gapped lobes at a density n equal to 1, n equal to 2, and n equal to 3. So the density meaning number of particles over number of sites, lattice sites. So n equal to 1 meaning total number of parts. Suppose 100 sites, that means 100 particles are there, 100 bosons are there. So you can see a clear phase transition if you go from this site to that side by increasing T over U. So you go from a large interaction to small interaction regime. So there is a phase transition at this point. And if you go to higher density, if your system has n equal to 2, so then you also go to another transition, Mi2 to superfluid phase through this boundary. Okay, so this is interesting. And if you go along this direction, along the y direction, by changing the chemical potential, that means you increase the chemical potential, that means you accumulate more and more number of particles in the system. Then also you go through different phase transition. That means this white region to gray region, which is a Mott insulating phase, superfluid to Mott, to superfluid Mott, and so on and so forth. So there also you see a phase transition. And the interesting thing to note here is that these Mott lobes are very well separated from each other. Okay, so every Mott lobe, two Mott lobes are separated by this superfluid phase in between. So this region is gapless, this white region is a gapless superfluid, and this gray regions are all gapped Mott insulating phases. Okay, so this is the key results from this simple model, which is a two-body interacting bosonic lattice model. Okay, only hopping and potential, on-site potential is there, on-site interaction. Now, suppose you, okay, so this is what I have just explained, that this is a Mott insulator, this is one particle in each site, this is Mott two particles in each site, and Mott 3 and so forth. Okay, suppose you say that instead of allowing only two-body interaction, if you allow for more than two-body interaction, like three-body interaction, higher order terms. Suppose you say that you have three particles sitting on a lattice site, and then they interact through a three-body interaction. So three particles can combinedly interact with each other. Then this energy of the system will be different. Now, instead of just 3U, you have 3U plus W. W is a three-body interaction. So that means it's a different system altogether. And this Bose-Hubbard Hamiltonian gets modified with this extra term, W over 6, Ni into Ni minus 1 into Ni minus 2. Okay. So this extra term can significantly modify the phase diagram of the Bose-Hubbard model, the earlier model that we saw, which had only Mott lobes. Now these lobes are slightly different from what we have seen in the previous case. These are like very sharp pointed things because this calculation is exact. Those are mean field calculation. These are exact diagonalization results. Therefore, these lobes are coming out to be perfect. And you can see this is Mi1, this is Mi2, Mi3, and so forth. So in this case, there is no three-body interaction. So therefore, you see a standard picture, which is Mi1 is larger than 2 and 3. But if you make a W finite and positive, you see that the Mi2 is significantly affected by it, and it has been enlarged quite substantially compared to Mott 1. But on the other hand, if you make a W attractive like this, then you see that this higher order lobes have shrunk quite significantly. It has become smaller compared to this one. Okay, so that means W, the three-body, one extra term in the system affects the entire phase diagram quite significantly. But the interesting thing to note here is that there is always this superfluid phase which is sandwiched between two gap phases. So here you can see this area is superfluid, this is Mott, and always there is a superfluid phase sitting within this between these two gap phases. Okay, now if you say that, okay, I can go on increasing the number of order of interaction to multi-body interaction, like I can write the Bose-Hubbard model like this. It's a general Bose-Hubbard model. I have this kinetic energy term, and this is the multi-body interaction term, which is UP. Depending on the value of P, I can go up to higher and higher order terms. For example, for P equal to 4, I have this model. So U3 is the three-body interaction, U22. So this is actually W. And then U4, which is another higher order terms, and so on. So if you restrict up to P equal to 4, then this is your Hamiltonian. Now, if this U equal to 4 is very, very strong, infinitely large, then this will prevent more than 3 particles on a single site. Okay, so that means this is a 4-body interaction. So if that means 4 particles, they will combinedly interact with each other with this term U4. If this term is very large, that means you are preventing more than 3 particles on a single site. Okay, so in that case, you can have maximum 3 particles on a site. And when you have 3 particles on a site, and then this term is finite, U3 is finite or W is finite. So that means a 3-body term U3 can effectively take a delta function form. So it is a delta Ni3. So whenever you have 3 particles on a site, then the interaction will be W. Of course, you will have 2-body interaction U. Okay, so that means this general Bose-Hubbard model under this condition can take this form. So I'm just talking about a special case of this general Bose-Hubbard model. When U4 is very, very strong, then you take this model takes this form, where U is the 2-body interaction. So again, I'm coming back to this notation. U3 is changed as replaced by this W, which is a 3-body interaction. So and there's a change of notation here. So tunability of U and W may lead to interesting physics that you have seen here. So if you can tune this W and U, then you will see these interesting features. And interestingly, there are proposals, theoretical proposals by various groups, they say that this interaction can be tuned in systems of cold atoms in optical lattices by the group of Sapabinaini and Baranov, and also in systems of superconducting circuits. So these are very new platforms to simulate quantum phases, superconducting circuits, very interesting platforms. Of course, cold atoms in optical lattices are very versatile, and it has ruled the entire last 20 years, two decades, more than 2 decades. Now many people are into superconducting circuits also. Okay, so if this can be tuned, then we may get interesting physics. And one of these very interesting prediction recently was this. It says that there can occur a first order phase transition in optical lattices with a tunable 3-body on-site interaction. So it says that in optical lattice, you can actually tune this 3-body interaction, 3-body on-site interaction, which is W. And if you can tune at certain regime of this interaction, then there can be a first order phase transition. So that means there can be a direct transition from one phase to other. It was by this group. And the prediction is for sufficiently large attractive W and repulsive 2-body interaction U. So attractive 3-body and repulsive 2-body interaction. This Mott insulator 2 lobe will disappear completely, and a first order phase transition from Mott insulator 1 to 3 occurs. So that means, as I already mentioned, that there are several Mott insulating lobes, Mott insulating 1 at density 1, Mott insulating lobe 2 at density 2, and so on. So it says that for sufficiently large W, this Mi2 will completely disappear, and there can be a phase transition from 1 to 3, direct phase transition. Okay, and this calculation is based on a simple mean field level calculation, and it is supported by rigorous quantum Monte Carlo results. Okay, so there are two methods being used. One is mean field level calculation. Using this, they predicted the phase diagram, and then they supported their calculation using rigorous quantum Monte Carlo simulations. So what is the result? So result is, this is the phase diagram of the usual Bose-Hubbard model without the 3-body interaction. W is 0. Just standard 2-body interacting Bose-Hubbard model. You have this Mi1, Mi2, Mi3, and Mi4 lobes. All these lobes are different densities. This is a mean field phase diagram. And then they said, if you increase W and make it very large and negative, this is minus 1.5 times the 2-body interaction, then this Mi2 lobe will completely disappear. So that is what happened here. You can see that this is the one section of this phase diagram. You can see that Mi1 here, Mi3 here, Mi2 has disappeared completely. Okay, so in this case, this Mi1 and Mi3 are connected directly with each other, and there is no superfluid phase sandwich between this. So there is a direct transition between this phase, this blue one to this pink one. Okay, so you can see that there is a direct transition at this dotted line, and these lines are obtained by using this mean field theory calculation, and they have supported their calculation using quantum Monte Carlo data. These symbols are quantum Monte Carlo data, these boxes. Okay, so these are quantum Monte Carlo data. These are these circles, and all these symbols are Monte Carlo data. So they are saying that for this condition, there is a direct phase transition or first order phase transition from Mi1 to Mi3 at this regime, this interaction regime. Okay, so this is a mean field calculation. This J is now the kinetic energy, which is T in our previous case. Z is the coordination number, which is used in your mean field calculation. Okay. Now, what we did, we revisited this model, the same model that they have used, and we tried to study the phase diagram, what they have obtained in a one-dimensional lattice. So they have this three-dimensional system, and we consider a 1D lattice system. And we use our approach, which is very well known for 1D simulations. For many body one-dimensional system is known as density matrix Riemann group technique, which is very powerful to analyze or study the quantum phases of one-dimensional many body systems. And the results we obtained is quite surprising. It is completely different as opposed to the earlier prediction by them. So you can see from this picture, this is the phase diagram obtained by us for 1D lattice. And you can clearly see that there is no Mott 2 lobe that they have predicted. Mott 2, Mi2 lobe completely has vanished. Surprisingly, there is no direct phase transition between Mott 1. This is rho equal to 1 is the Mott insulator 1 lobe, this pointed one, and this is Mott insulating 3 lobe. So there is no direct overlap of direct transition from 1 to 3. Rather, there is a superfluid phase. There is a gapless region sandwiched between these two phases, which is completely contradicting to their prediction, which is this is their result. Here there is a direct transition from here to here, but here we are getting, on the left side, we are getting a superfluid phase which is sitting between these gapped phases. Okay, but this is 1D, this is 2D. Now, just to confirm what phase is this region, superfluid region, here we try to compute the different physical quantities. The one of these important quantities to distinguish this phase, to identify this phase, what is there, what is sitting there in between these two gap lobes, is to find out the number of particles the system can accumulate if you increase the chemical potential. So along this direction, the chemical potential is being increased, and we are trying to see how the system is accumulating particles. If it is an usual atomic bosonic superfluid, just a superfluid, then at every step, if you increase the chemical potential, the system will accumulate only one particle at a time. But here, what we are seeing here, by increasing the chemical potential, you can see that the density equal to 1 plateau is the correspond to this Mi1 lobe. So if you go away from this lobe by increasing the chemical potential, here we are seeing that the system is accumulating 2 particles at a time. So instead of accumulating 1 particle at a time, it is actually favoring 2 particles at a time. So this jumps in densities in steps of 2 particles at a time. Then at this point, it again accumulate 1 particle at a time. Then further at this point, this region, it accumulates 2 particles at a time. So that means if you, this point is actually a cut through the phase diagram like this. So we are increasing the chemical potential along this direction. So when you cross density equal to 1 lobe, which is somewhere here, and then we enter this phase, this region, and then in between there is the superfluid phase, this one, we call it an atomic superfluid or a plane superfluid. And then it enters another region where this system accumulates 2 particles at a time. So that is actually a signature of a pair superfluid phase, or a phase where this bosons, they actually remain as pairs. They form bound states. Okay. So this signature of accumulation of 2 particles at a time is a signature of a paired state formation. So this is something surprising because we assumed 2-body repulsive interaction, but here we are seeing a signature of 2-body bound state, which is a little bit counterintuitive because of repulsive 2-body interaction. But we further confirm that this is indeed true. The system is in the paired phase, because then we computed this pair correlation function and compared it with the single particle correlation function. Here you can see that in GP in those regimes is dominating this colored, this red and blue curves. With this is the correlation with respect to distance. They remain finite. They decay slowly as compared to this single particle correlation, which falls off rapidly at those points. Okay, of course, this green one is the single particle correlation, which is finite in this region, this superfluid region. This is the single particle superfluid. This indicates a pair superfluid behavior. And this one is the exponential fall of the correlation function. So that means there is no single particle correlation in this region. Okay, so this means a pairing of bosons even in the presence of 2 particle repulsion. Are we getting a repulsively bound pairs, because they are repulsing they are repelling each other, but still we see some signatures of bound pairs. Okay, so we also confirm this by computing other order parameters like parity order and fidelity susceptibility to see this phase transition. I will not go into the details of this, but we indeed see a phase which is sandwiched between the lobes. This is actually a zoomed in part of this. So that means there is no direct jump between these 2 gap lobes, but rather there is a phase which is sandwiched between these 2 gap phases. And this phase is actually a phase of paired bosons. So it is a paired superfluid phase. Okay, it's a superfluid of bosonic bound state. Okay, so this means we are saying that this prediction by in this paper is whether it is correct or not correct. But we have to now wait, because our simulation was in 1D and this calculation is in a 2D platform. Okay, so we need to verify this calculation in a 2D system as well. To do this, we moved on to two-dimensional system. Their calculation was based on conventional mean field approach, which does not get proper correlation effects. But what we did, we moved to a different scenario, which is known as the cluster mean field theory approach. And this is a little bit more versatile compared to this simple mean field approach. The simple mean field approach is based on single site mean field decoupling scheme, where the entire many body system is approximated as a single site Hamiltonian. But what we have done in this method, this cluster mean field theory approach, we divide the entire system into small clusters instead of single site. So each cluster can be treated as exactly. So therefore, one can incorporate some correlations in these small clusters, and hence this has more accuracy compared to the single site or simple mean field approach. Okay, so using this cluster mean field Hamiltonian, this is the cluster mean field Hamiltonian, we try to perform our simulations to predict these phases, to predict the to confirm the prediction of paired superfluid phase and no first order phase transition in 2 dimensions. And the result is surprising again. This is the phase diagram in 2D using our CMFT approach. This is their result. So if you compare, again, there is no first order transition. So there is a hidden PSA phase or sandwiched PSA phase in this phase diagram. So this means in 2D also there exists no first order transition as predicted earlier. A paired superfluid phase exists between this MI1 and MI3 lobes for large interaction, for strong interactions in this region, okay, which is not here, which is a direct first order transition in this case. So this is interesting because this is a simple Hamiltonian with only on-site interaction. And we have used two different methods in two different dimensions, and we predicted a different physics compared to the other predictions using Monte Carlo and mean field approach. Then people will not believe why, I mean, how can you counter a quantum Monte Carlo calculation with this simple mean field type simulations? The question is valid. To justify this, we try to perform, we try to compare the cluster mean field theory calculation versus quantum Monte Carlo data. We extrapolated, we just extracted their data from the paper. So these boxes are quantum Monte Carlo data from their paper, for example, this one here, and try to compare our results using cluster size extrapolation. So that means you take larger clusters with more number of sites, bigger clusters, and you perform a finite size extrapolation to see how it is matching with quantum Monte Carlo data. So here you can clearly see that it is not matching. These crosses are, the cross symbol is our extrapolated data by using 2 site, 4 sites and 6 site clusters. Clearly you can see that it is not matching. But this is not the region of concern, because these regions are tip of the Mott lobes where kinetic energy dominates, and where kinetic energy dominates, mean field will not work, because we are excluding the effect of correlation. We are simply considering the correlation effects within the cluster. So there it will not match with the Monte Carlo data. But our region of concern is large or strong interactions where kinetic energy is dominated by interaction. And here you can see that the data is matching perfectly well with the Monte Carlo data. The box and cross, they superimpose with each other. For example, here, this is the region of interest. And in this region of interest, we are matching very well with the Monte Carlo data. But of course, we don't match at this point, and we don't care about this point also, because we are talking about this region. So if you compare now, our prediction is correct. Okay. And we find, I mean, using this simple CMFT approach, also we find the signature of pair superfluid phase in between these two Mott phases. Further, we used the technique based on tensor network states, and we further confirmed that there indeed exists a pair superfluid phase. And this is even much more powerful in two-dimensional systems. And this prediction is confirmed by using three different methods. Okay. So this says that this is not correct. This first order phase transition is incorrect. That means there is no first order phase transition in this kind of system. And the wrong results of this paper could be due to some numerical artifact. Okay. So the key results so far that the two body repulsive bosons, they move together in presence of a three body attraction. Okay. It's a very simple system, but the physics is novel. And let us try to understand why we get pairs in this case. Why, I mean, how can you expect a pair in this kind of system? Because these are repulsively interacting particles. Now consider this simple picture. It's a one-dimensional Mott insulator at a density equal to 1. Then suppose you have two more particles on top of this one-dimensional Mott insulator. These two added defects, two extra bosons, they experience uniform MI background. So that means when these two particles, if they go here, this energy of the system will not increase because they will experience the same potential from all these particles, all these bosons sitting in different sites. So therefore, instead of forming a trimer due to attractive interaction at a single site, instead of forming a three-body bound state, these two bosons, they prefer to move around in this uniform background of bosons. Okay, so that means they behave like this. So they can simply jump to a different sites as a pair of particles because system energy doesn't change. The Mott insulator background is uniform, so therefore they can simply go around in a form of pair. Okay, so this is the mechanism why we see a pair just above this Mott lobe. This Mott 1, this is the Mott lobe at density equal to 1. Excuse me. Sorry. Yeah. So this is the Mott insulator, two Mott insulating phases, which are sandwiching the PSF phase. Okay, so this mechanism is understood by different calculations in different dimensions. Now, this idea seems very simple because one can simply understand it like this. Two bosons, they are fighting with each other because they have repulsive interaction between them. Then you introduce another boson and then they start liking each other. So, I mean, this is just a cartoon representation of the mechanism here. Okay. Now, the next part of the talk, where we are trying to simulate this, or we are proposing whether this can be simulated using a quantum walk experiment. Okay, so as I mentioned, this quantum walk is just a dynamical evolution of a few particle state, and it is very a powerful tool, and it was first proposed in 1993 by this group of people based on the concept of classical random walks. So this is called quantum random walk. So random is not correct here because this is quantum walk, just quantum walk. So they introduced this concept and show that due to quantum interference effect, the average path length can be much larger than maximum allowed path in the corresponding classical random walk. So this is a different, this is a very interesting concept. They say that if you have quantum mechanical particle and they perform random walk on a lattice or on a graph, then their spread is much faster compared to the quantum walk due to quantum interference effect. And just to compare these two mechanisms, one is classical. Here you can see that this quantum walker, classical walker, is performing some random walk on this lattice. And after a long time evolution, you can see that this walker's position doesn't change substantially. The spread is limited to the origin or the place from where the walker had started. But in the case of quantum walk, you can see that this walker spreading is quite vast. It has spread to a very large portion of the lattice within this time period. because of this superposition principle, quantum superposition principle. And if you just want to quantify this, you can see the probability distribution of a quantum walk and classical random walk. The black one is a classical system. And this probability spreading is limited to origin after a long time evolution, maybe 1,000 steps. And if you look at the variance sigma, it actually goes as square root of n, which is number of steps in this quantum in this walk. But if yes, question? No. Should I continue?
I don't think it's a question. Just go ahead. Must be in some.
Okay. Okay. So in the case of quantum walk, this is something interesting. You can see the spreading of the probability, which is very wide in this case. So this variance goes directly as n, and this probability spreading is ballistic in nature in the case of quantum walk. So there are different versions of quantum walk. You will hear more about this in the talk of Professor Colin Benjamin, I think tomorrow or day after tomorrow. He will discuss about different types of quantum walk. So there are two here, discrete time quantum walk and continuous time quantum walk. So this happens in discrete time space. This happens in a continuous time space. So here you require, you go from some initial state, phi I minus 1 to a final state. By performing these operations. One is shift operator, one is coin operator. So that means you create some initial state and then you create some superposition of state. And depending on the coin operation, you go to the left or right, left and right like this. And this happens in a discrete space. But in the case of continuous time quantum walk, this happens in a continuous time space. And here, this initial state goes to a final state through this unitary time evolution. Okay. So there is a well-defined, well-structured theory behind this, but this is a very simple concept. So both these quantum walks, they require some initial state. They start from some initial state, and they give identical final results. Okay, but this continuous time quantum walk is more convenient, as this time can take a continuous value, and the Hamiltonian is time independent, and this is a simple unitary time evolution. So it turns out that this quantum walk is just a simple unitary time evolution, and where you start from some initial state psi 0 and time evolve it with this unitary operator, and then you go to a final state psi t. Okay, so the key ingredient is some initial state, and then you go to a final state. So this is something kind of a fast quenching. Okay. This is the example, simple example with just one particle and a periodic potential. This is a graph, this is the particle, and you perform this time evolution of state, and then you compute the observable, for example, Ni, number density with respect to this time evolved state psi t. This is the theory. This axis is the first initial state. You have lattice, and then the initial position of this particle is at the center of the lattice, and this is the maximum density here, which is 1. And then as time goes on, you see that the spreading of this particle, which is spreading very fast. So this cone type, light cone type behavior you can see. So this probability is spreading very fast. And this has been experimentally observed recently using cold atoms and optical lattice in the group of Marcus Greiner. They have these techniques of single site resolving spectroscopy, imaging spectroscopy. They can image the particles' positions in different sites, so you can see a clear matching of this spreading. Okay, and in the recent past, there have been several experimental observations in various different systems like trapped atoms, ions, photonic lattices, waveguide arrays, superconducting processors, even in photosynthetic excitations, and so on. So these are the papers, and there are many more in recent years. But the interesting thing happens when you have more than one particle, and you study quantum walk. So due to quantum effect, due to this interplay between wave nature of particle, quantum statistics, and interaction between the particles, you may find novel quantum phenomenon in the context of interacting quantum walks. So there are several experiments in different contexts. For example, photons in waveguides, cold atoms in optical lattices, superconducting circuits. They have obtained various interesting phenomena of interacting particles in quantum walk. And of course, there are theoretical proposals to have universal quantum computation using interacting quantum walks by Andrew Child and all. Okay, so the key ingredient in all these processes, all these experiments and theories are like bosons in periodic potential, which is very suitable for our system. So now let us see if we can try to reproduce our finding using interacting quantum walks. So before going to our systems, let me try to highlight the quantum walk of two interacting bosons in one dimension, because ours will be a different case. Let us try to study the see the simple case, that is two interacting bosons in a periodic potential. So two interacting bosons are sitting at the center of the periodic potential. So this initial state can be like this. This is zeroth side. You are creating two particles at the zeroth side like this. And then you have this Bose-Hubbard model, because this can be explained by this Bose-Hubbard model. They can interact via this interaction U, and this particle can tunnel to different sites. And we can perform this evolution. For small u, since there is no interaction, kinetic energy dominates. So they perform independent particle quantum walk. So this quantum walk is similar to a single particle quantum walk, because these particles are not interacting with each other. So effect of interaction is negligible. And the spreading will be fast, because these are single particle quantum walk. They can spread faster. And if you compute the diagonal this correlation matrix, then you can see this diagonal as well as off diagonal correlation matrix elements like this. But if interaction is large, they form these two particles. Actually, they form bound states. They form effective two particle quantum walk that I'll discuss. And since they are forming a bound state due to this interaction, then these propagations will be slower. Instead of this fast propagation, they will slow down, and you will get a dominant diagonal correlation matrix elements that I will show you here. So this is the example. Here, this is a single particle quantum walk. You can see a fast spreading of probability over here. But if you go to a two particle system, suppose you created these two particles at the center of this lattice, and then they are moving to the left and right simultaneously. When U is 0, they behave like single particles because they don't talk to each other. There is no interaction. They're indistinguishable. So this profile is fairly similar to this profile, single particle quantum walk. But if U is very strong, that means they are repulsively interacting with each other, then they form an effective two particle state. And since they are forming an effective two particle state, their kinetic energy is suppressed. So therefore, they perform a quantum walk with slower dynamics. So you can see that spreading is very slow compared to this. So they haven't reached up to second, third sites after this time evolution, right? Okay, so this has been experimentally observed by the group of Marcus Greiner by looking at this correlation matrix. Here you can see that for small interaction or weak interaction, this correlation matrix indicates the interference of this matter wave. Here you can see a very nice interference pattern at every corner of this correlation matrix. But for large interaction, you can see that since they are forming a bound state, only these diagonal elements survive, the diagonal correlation survive. So this matches pretty well with this experiment, theoretical calculation over here. Okay, so this is just two particles on an empty site. So two particles, they are performing quantum walk on an empty site, empty lattice, and they exhibit this kind of phenomenon. Okay, they form pairs, they move together by exhibiting slow propagation in their quantum walk, and this has been experimentally observed. Now, in our system, we have a different scenario. We don't have two particles on an empty site. We have a different concept. Can we capture the physics predicted by using a many-body state in the context of quantum walk? So our system is this. We have this phase diagram, and we want to predict the existence of this paired superfluid phase or pairing mechanism using quantum walk. So that means our focus area is here, just within this two lobes, just between this MI1 and MI3 lobes, because this pairing occurs somewhere here. And to reach at this point, to create an initial state corresponding to this regime, we need to go above the MI1 state, because this lobe is MI1. So that means every site is occupied with one particle at each site. And if you want to go in between this, then you have to dope the MI1 state. That means you have to add more particles to this state. So the minimum initial state that one can create two local defects on top of an one-dimensional Mott insulator state. So that means you have this 1D MI state, one particle at each site. Then you dope. You just add two more particles because you want to see this repulsively bound pair state. So you can just add two extra particles, and this is your initial state. Okay, so you created we created two particles at the 0th site, that is the central site. So this is the initial state. Okay, MI1 1 1 1 1 1, and then suddenly we have three particles at the central sites. And we have to perform the quantum work. We have to perform the dynamics, and this is our Hamiltonian, and you perform the dynamics like this. And with this dynamics, this is a complex problem. So there is, I mean, we can have exact solution, but we cannot match, we cannot get appropriate results. So therefore, we use very sophisticated method known as time evolving Bloch decimation method, which is a method based on matrix product states. And our regime of interaction is repulsive U and attractive W again, because same thing that we have used for our many-body calculation. And the diagnostics are on-site density and correlation matrix. Okay. Now you can see that here what we have done, we have fixed U at 10 and the J, that is the kinetic energy, at 0.2. So that means the ratio is very strong to maintain the Mott insulator background. So this maintains the Mott insulator background because U is very, very strong. That means every site will have one particle. And then we increased W from 0 to very large value on the negative side, so attractive side. Okay, we started from 0, and I have not shown 0 here. We have shown minus 0.5 times U, and we have gone up to minus 1.5 times U. Okay, so that means you are going from small w to large W, and we are seeing the spreading of density at each value of W. So you can see that W is unidirectionally increasing, but the feature shown here is something interesting. So we are seeing a very narrow profile, so very slow spreading of density over here, which becomes faster gradually as W increases. And then it again becomes slower further as W reaches minus 1.5 U. So note that U is fixed, W is just increasing, but this is showing a different behavior. It is not spreading more and more, rather it is becoming faster from slower and then again becoming slow. It's kind of a re-entrant signature. It goes from slow to slow through this fast process. Okay, so this is something interesting. But now you can already see that this slow spreading of density can indicate the formation of bound state that we have already predicted for this value of W in the many-body case. Okay, in the many-body case, we have already seen that for this limit of W, we have a bound state formed already. And in this case, in this simple case also, if you have a Mott insulator background and you have two more defects on top, for this value of this minus 1.5 of U, you can still see that this has already formed a bound state, because you can see this slow propagation. But here also, interestingly, for small w, you can still see a bound state function. I mean, it's a slow propagation of density. This is something very interesting here and here. Okay, now we can clearly say that this quantum work can actually predict the simulate the prediction of a many-body system, or the physics of a many-body system, with this simple few particle dynamics. So because this dynamics is just, I mean, you have uniform background and we just created two extra defects in the system. To quantify this further, we compared our results with this correlation matrix. Here you can see that the diagonal entries are finite and large. That means this is a signature of a paired state. And after you increase W further, then this pair starts to break, and then you get complete interference pattern, which is a single particle dynamics. And then again, you will re-enter into this paired state. Okay. Sorry, it's actually raining heavily here, so this outside thunderstorms you can hear. Okay, so we go from paired state to another paired state through this unpaired or single particle dynamics. Okay, so this is a reversal of phenomena or quantum walk reversal phenomena that we have predicted in this, we have reported in this article. Okay, now let us try to quantify it further. We all know that if a quantum mechanical particle is subjected to some external force, then that undergoes a periodic or breathing motion in the lattice, in the position space. So this is known as the Bloch oscillation, and this has been experimentally seen again by the group of Marcus Greiner. Here you can see this is the Bose-Hubbard model, and some external electric field or tilt has been applied. This is the tilted lattice, and if you have weakly interacting particles, then they, I mean, due to this periodic tilting, you can see this nice breathing motion of particles, which is known as the Bloch oscillation. But if you have a strong interaction and these particles, they form bound states, local bound state, then this periodicity of oscillation that gets doubled. So you get this 2 beats within this one big envelope. Okay, so this is a theory, this is experimental observation, and this period of oscillation depends on the strength of this tilt. Okay, and we try to compute the Bloch oscillation in our case. Here you can see that compared to this, if you just compare the top panel with this bottom panel, you can see that this is there are 2 beats in between this time evolution time, and gradually you can see this envelopes, they get widened, and finally they disappear. This node disappear, and you get a single envelope, and then you go again into this 2-period oscillation. Okay, so that clearly indicates that there indeed exists a bound state or bound pair of bosons in this case. And if you compare everything together, clear signature of bound pair formation at 2 extreme ends of W, small w and large W. And this is a reentrant or reversal phenomenon in the quantum walk of interacting bosons. Okay. Now we have already discussed why these 2 extra defects, they form bound states because of the mechanism that they are moving on top of a Mott insulator background. Then the question is why this bound state forms, why there is a bound state at W equal to 0.5 or W equal to 0. Even at W equal to 0 also there is a bound state. So this is this has been already discussed in the context of 2-particle problem. If you have a Bose-Hubbard model, because 3-body interaction is 0, so you have this model and you can solve this 2-particle problem with some effective center of mass problem. Then you obtain for weak interaction, you see this scattering states and bound states are superimposing with each other. So there is no separate bound state. But if you have a strong interaction, then these bound states are largely separated from these scattering states. And due to this bound state cannot actually break into individual particles. So therefore, these atoms, they actually stay in this bound state and move together as a pair state. So what does it mean? If the interaction is very, very large, very, very strong, and 2 particles are sitting on top of each other, then if they want to dissociate from each other, then the energy released will be on the order of this interaction, which is very large. And this energy released has to be converted to kinetic energy. If this kinetic energy is very small, then this is an off-resonant, non-resonant condition. So this energy, interaction energy, which is released by breaking this 2-particle state, cannot be converted to the kinetic energy. Okay, so hence these particles, they prefer to stay together and move together in a lattice. So this This is known as the repulsively bound pair, and it's a very interesting artifact, a very interesting manifestation of this bosonic particles on a periodic potential. And this has been experimentally observed. You can see that here normalized pair number is plotted with respect to hold time. So they created this atomic cloud on an optical lattice, and for two different interaction strengths. So this indicates interaction strength in cold atomic system. These are S-wave scattering lengths. 100 is strong, 0 is zero interaction. So for the case of zero interaction, you can see that number of pairs that gets reduced substantially as time evolves. But if the interaction is very strong, then this pair number remains quite substantial, quite large after a long time evolution. So this has been reported in this paper. It's a very interesting prediction known as repulsively bound pair, only with two particles. I mean, it's only with Bose-Hubbard model with two particle interaction. But in this case, we have a Mott insulator background. So these two particles, they feel like they are on an empty site. Okay, so because of this uniform Mott insulator background, so they feel that they are on an empty lattice site, because there is no three-body interaction here, W equal to 0. So this scenario is same as this scenario, two particles on empty sites or two particles on an uniform background. So that means that the entire potential of the entire system has been lifted by some factor. So it doesn't change anything. Okay, so this is the mechanism behind why we get a paired phase at W equal to 0 or small w. Okay, so this is the prediction that we have done. What we have done so far is that we have shown that bosons with repulsively two-body interaction and attractive three-body interaction may form two-body repulsive bound pairs. And this mechanism provides an alternate approach to form pair superfluid phase of repulsively bound pairs. I showed one approach here where they have shown repulsively bound pair. But here we are saying that you can actually create a pair superfluid phase in a controlled manner. You can select the number of particles in your system, whether you want a 2-particle pair superfluid phase or 4 particles pair superfluid phase or 80 particle pair superfluid. So you can actually control the system. How many number of bosons you need to create a pair superfluid phase, that can be controlled in this kind of approach. And our prediction contradicts the earlier prediction by the group of Sapabina et al., the paper I showed, that a first order phase transition between Mott lobes occurs in interacting systems. So our proposal can be experimentally observed using quantum walk of Mott insulator defects that I showed. I showed how this can be experimentally, I mean, if one is able to perform this experiment in some system, then this can be really predicted. This many-body phenomenon of repulsively bound pair can really be observed in experiment, in the quantum walk experiment. So in such a scenario, a phenomenon of quantum walk reversal has been predicted. We showed that how a quantum walk reversal can happen in this simple system. And in principle, this can be observed in possible superconducting circuit. I mean, this is possible to observe in superconducting circuit experiments, because in optical lattice experiment, it may be difficult to observe due to scattering or losses of three-body interacting system. But I think in superconducting circuits, one can manipulate the non-linearity on anharmonicity to create to keep higher level up to 3 or 4th level energies to tune these interactions independently, so that one can see these interesting features. So these are the papers I cited in this talk, and the people who work in these projects are my former student Suman Mondal, who is now a postdoc at Göttingen, and my former postdoc Manpreet Singh, who moved to Paris after finishing a postdoc position here in Guwahati. These are all people worked in Guwahati, and my collaborator Sebastian and Augustine from Berlin, Sebastian from Geneva. So thank you very much. If you have any questions or suggestions, you can always ask me or tell me.
Yeah. Thank you very much, Tapan, for this nice talk. Do students have any question? I have a couple of them, but let students ask first. Maybe as we are waiting. So this it's kind of interesting how you are building this three body system. The I believe that the interaction is still pairwise, right? It's not like any FMO kind of a
No,
system.
no, 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 no.
It's
This
kind
is
of
just,
interesting.
I mean, three particles, they interact with each other simultaneously, that I showed here. Yeah,
But
so if you follow this paper by Baranov,
okay,
it's a very nice article. Yeah. Let me go back to that paper.
but when you have only two, there will be repulsive between them.
Yes,
That's
yes, yeah, yeah. So this paper, Misha Baranov actually shows how to control this interaction independently, even higher order interaction also. Yeah, but this paper, in the paper Sapabinaini, they showed they can actually link this state to some FMOP state by using some microwave something. I have forgotten the technique how they do it, but yeah. So they can map it to some FMOP states
states. Okay.
and then tune it. Yes.
Okay. The other thing is in one of your things in the lattice you have only two particles,
Hmm.
but somehow you are able to construct the three body state. I was not very clear on that part.
Where? In which slide? Can you?
It's one of the later slides when you are showing your work.
Yeah. Here.
Next one.
In the dynamics. Okay.
In the dynamics.
Yeah.
You,
Here or here?
no, there was a picture of lattice where there was only two particles in the lattice, not three, but it's interacting
Here.
with neighbor. This and the next few.
Okay. So this one maybe.
These
This one.
ones. These ones. How does it? It seems to mimic the three body
No, 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 no.
problem.
So this is no, no. This is just an example with two particles only. So I have showed a system where we have only two particles and they are performing quantum walk. So there is no concept of three particles here. So only this, I have created two particles at the center
Okay.
and they have the equal probability to go to the right and left. So this is the quantum walk of just two particles.
Okay. Okay.
Yeah.
I don't see much
Yeah.
questions from somebody wanted this PDF that probably
Yes.
organizers will take care of. Um, Participants can unmute to ask questions. Please go ahead, participants.
Um,
Yep.
Can I ask a question?
Sure.
Yes. Professor there, yes.
Yes. So sometimes this three-body interaction leads to loss of atoms
Yes.
from the trap.
Yes.
So can you extend your studies to dissipative systems, including loss?
Yeah.
And say a driven dissipative system, and still you can get these results
Yeah.
in the long time limit. Okay.
Yeah. So I mean, in between we were thinking to do this, but then these are really difficult problems because these are bosons, and to simulate this closed quantum system, these numerical simulations are really difficult. And of course, one can easily perform this open quantum system. I mean, with dissipation and loss. But and as you said, experimentally in cold atom experiments, these are very important because you cannot avoid loss. And it will be really nice to see. I mean, I haven't done yet, but we have been thinking how to do, because open and the closed system itself is very difficult. The numerical simulations are, because these are bosons, so you require the local Hilbert space to be very large to see this dynamics of two particle superfluid phase. But yeah, one can in principle include dissipation and see whether they survive. That is why I thought superconducting platform will be more suitable, because there this collisional loss or three-body loss is not there. You have microwave photons, and I think, yeah, that superconducting system itself is a lossy system. But if you can pump the system continuously with photons, probably you can access.
But then you can think of two-component fermions in the lattice.
Yes.
And you can see whether you can simulate fermionic superfluidity through Cooper pairing and
okay. I see.
So it will be analogous to superconductivity.
Okay.
Yes.
This cluster calculations you are doing, have you played around with the size of clusters?
Yes.
Like if you go on increasing, it keeps changing, and after some time it doesn't make any difference.
I showed you some results here. Here, this one. You can see that this green one is 2 sides result. And then this triangle, blue triangle is 4 sides, then red one is 6. Yeah. So 6. Then this is the extrapolated one. The cross is extrapolated. Yeah. So more number of sites in a cluster will give you more accurate result, but then it is difficult because you have to treat the cluster exactly. So you need to have sophisticated exact diagonalization technique.
Right. So it becomes computationally more.
Yeah, computationally.
Yeah. There is a raised hand, Saurabh Sharma.
Saurabh Sharma. Go ahead, Saurabh. Sorry, you can unmute and you will have to ask. You can unmute yourself.
Saurabh, you can unmute. Then maybe can I ask one question?
Sure.
Yes.
See, Tapan, in the ITC days, early 80s, T.D. Lee had a model, where bound states of fermions, used to condense.
Okay.
So this was an alternate model for ITC, paired kind of thing, that repulsion was playing a key role. So this intuitively repulsion is playing a key role. See, for example, Wigner crystal, repulsion plays a key role. Because I'm not still able to get intuitively, repulsion playing a very key role. Is there any way one can sort of understand it?
Yeah, so here, if you don't take repulsive interaction, for example, suppose we switch off the repulsive interaction here in this case. So what we get is a 3-body bound state. So just a trimer. So, I mean, just to understand the effect of 3-body interaction, so sorry, 2-body repulsion. So suppose you remove this U here and this one. So this 3 particle will form a trimer.
Okay.
And suppose you make U negative. You make attractive 2-body interaction. Then again it will form a bound. Altogether a bound state. W attractive and U attractive. Then that again you have a trimer. Because 2-body attraction will favor a trimer again.
Right.
But since U is repulsive, this is the key point actually. U has to be repulsive. Otherwise you cannot see this.
Okay. Got it. Thanks.
Right. If there are no further questions, we will thank Tapan again. Thank you very much.
Thanks a lot.
Thank you.
Right. and we'll go to the
Yeah.
next one. Gautam Pal is waiting. So let me very briefly introduce Gautam Pal. I want to give